Hi there. In this video, we're going to be talking about AP Chemistry's topic 4.8, Introduction to Acid-Base Reactions. Acid-base chemistry is a really big topic, and this is just going to be a brief introduction to some of the basic concepts in acid-base reactions. You'll hit a lot more of it in Unit 7 of the AP curriculum, but this is just going to be a brief introduction on the reaction side of acid and base reactions. So when we talk about acids and bases, there are a couple of different definitions that we look at. The first one we're going to talk about is the Bronsted-Lowry definition. The Bronsted and Lowry were two different scientists that came up with this definition contemporaneously, and so it's named after both of them on how acids and bases behave. Because originally acids and bases were just defined by their physical and chemical properties. So if a substance tasted sour, if it reacted with metals to produce hydrogen gas, if it fit a certain amount of physical and chemical criteria, then we called it acids. But what made it an acid was what Bronsted and Lowry came up with. And Bronsted and Lowry said that acids donate a proton. And just a reminder, a proton is a hydrogen ion. Remember, hydrogen has a proton and an electron. And if it loses its electron, then it becomes positively charged, and all you have left is a proton. So acids donate a proton. Bases, of course, are the opposite. So what would a base do? Well, if acids donate protons, then bases accept protons. And so this definition explained why acids behave the way they do and why bases behave the way they do on a molecular level. So let's just look at a couple of examples here. Let's take some HCl, hydrogen monochloride, and let's put it in a solution that has hydroxide ions. If I do this, what will happen is that the hydrogen will be lost by the HCl and be gained by the OH minus. So what's going to be left behind is Cl minus because it lost this positive hydrogen ion. So the chloride was left behind, and the hydrogen transferred to the OH, and we made water, HOH, which I'm going to write water as HOH rather than H2O to show that the hydrogen attached itself to the hydroxide, the OH. So if you'll notice, this substance gave away a hydrogen, and this substance gained a hydrogen. So that, by definition, makes this an acid and this a base. Let's look at another example. HC2H3O2. This is hydrogen acetate, and let's say we put it into a solution of ammonia. Ammonia is a really common substance. It's used to make fertilizers. It's used in Windex to clean your windows. It's a very important compound chemically and industrially and agriculturally because it is used to make fertilizers. Anyway, in this particular reaction, the hydrogen will get transferred from the hydrogen acetate to the ammonia. And when it happens, we'll end up with C2H3O2, and that will now be negatively charged because it lost the positive hydrogen. It was neutral, so that means now it has a negative charge. The NH3 was neutral. It gained a hydrogen ion, and so now it's NH4 with a positive charge. And so this substance, hydrogen acetate, lost a hydrogen. This substance gained a hydrogen. The hydrogen went from here to here. So by definition, that makes hydrogen acetate an acid, and that makes ammonia a base by the definition of Bronsted-Lowry, because this one gave away a hydrogen, this one gained a hydrogen. So you might be, well, let's do one more, OCl minus. So here's another polyatomic ion that is in solution, and let's say that we put some HBr in there. So what's going to happen? Well, when this reaction takes place, a hydrogen leaves the HBr, transfers over to the OCl minus, meaning that we'll get HOCl, since the OCl was minus, and we added a positive to it, now it's neutral, HOCl, and the HBr lost a positive hydrogen, so what's going to be left is Br minus. So again, by definition, the substance that lost the hydrogen is the acid, the substance that gained the hydrogen is the base. So you might be asking yourself, how do I know how these things occur? And the answer is you have to know what the acids are. You have to know some common acids and know how they behave, and then common bases also. So there's some patterns here. If you'll notice, negative ions a lot of times are capable of accepting H positive ions because a negative will attract a positive. So a lot of times, polyatomic ions that have a negative charge can act like bases. And you'll talk a lot more about that again in Unit 7, but not quite yet. But just kind of a preview, negative ions a lot of times can accept those hydrogen ions and act like bases. Acids often always have a hydrogen ion. And because remember, by definition, acids give away a hydrogen. So if a substance has a hydrogen ion that can come off, then it can behave like an acid. So that's a quick lesson on how you know what's going to happen in an acid-base reaction. But again, you got to memorize some things. So strong acids, just to remind you, are HCl, hydrochloric acid, HBr, hydrobromic acid, HI, hydroiodic acid. These are all the halide acids because they are the halogens bonded to hydrogen. Notice that fluorine's not in here. HF, hydrofluoric acid, is not a strong acid. It's a weak acid. And we'll talk more about that in just a second. Now we got some oxyacids, nitric acid, HNO3, perchloric acid, HClO4, and sulfuric acid, H2SO4. These are the strong acids that you should be familiar with. And what strong means is that each one of these substances, when placed in water, will lose 100% of their hydrogen ions. So in other words, they will what's called ionize 100%. Every single molecule of HCl will lose its hydrogen ion when it's placed in water. Every single hydrobromic acid molecule will lose its hydrogen ion when placed in water. And these are strong because of that 100% ionization. Weak acids, on the other hand, some of the hydrogens will come off, but a lot of the hydrogens will actually stay attached to their anions and won't ionize. So strong acids, every molecule ionizes. Weak acids, only some of the molecules ionize. Okay, strong bases. So the strong bases are fairly easy to remember. They are the alkali metals bonded to hydroxide. So LiOH, NaOH, KOH, RbOH, and CSOH. So, and they're just called their ionic names because these are ionic compounds. Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. Those are strong bases. And then two of the alkaline earth metals are also strontium hydroxide, SrOH2, because strontium has a 2 positive charge, and barium hydroxide. So those are the strong bases that you need to be familiar with. And then two weak acids and bases that you really should be familiar with. A weak acid, HC2H3O2. This is acetic acid. It also is often written as CH3COOH, chiku. And so you can write it either way. This is the hydrogen that comes off when it's written this way. This is the hydrogen that comes off when it's written this way. Organic chemists usually write it this way because this is the order that everything's bonded. Inorganic chemists will often write it this way because it's a positive ion bonded to a negative ion, hydrogen acetate. That's a weak acid, very common weak acid found in vinegar. And then a weak base, very common weak base is an H3, and you should be familiar with that also, ammonia. So weak acid, weak base. So these are strong acids, strong bases. Once you know those, then you can start predicting how the acids and bases behave. The next thing I want to talk about when you look at all this is we identified the acids and bases, but what do they become over on the product side? So if you'll notice, the HCl was an acid, but it lost a hydrogen. Once it lost a hydrogen, it became the chloride ion, and that is called the conjugate base. Conjugate base. The acid becomes the conjugate base after it loses a hydrogen ion. And these two together make what's called a conjugate pair. So the acid, after it loses hydrogen, becomes a conjugate base. The base, after it gains a hydrogen, will become what's called the conjugate acid. And that is the second conjugate pair in this reaction. So conjugate pair also. So there's always two conjugate pairs in these acid-base reactions. The acid becomes the conjugate base, one conjugate pair, the base becomes a conjugate acid. So let's look at this bottom one, see if you can identify the conjugate acid and conjugate base. Okay, so here's the base. After it gains a hydrogen, it becomes a conjugate acid. So here's our conjugate acid. The acid, after it loses the hydrogen, becomes what's called the conjugate base. And so there's the two conjugate pairs, the acid with its conjugate base and the base with its conjugate acid. Those are things that you will need to be able to identify in chemical reactions. And just so you know why it's called that, if we ran this reaction backwards, which substance here would be able to give away the hydrogen? The acid. So the acid would give the hydrogen to the base, and that's why this is called the acid now, and this one's called the base now. The last thing that I just want to talk about in here is the important role that water plays in acid-base chemistry. Acid-base chemistry has to occur in water. That's an important part of acid-base chemistry, is it always occurs in solution. So if we have some HCl, which now you know is a strong acid because it's in the strong acid column, and I put it into water, H2O, what's going to happen? Well, remember, water, if we think about the structure of water, water has two lone pairs that are very, very negative. This is a very polar molecule, and that negative side of the water molecule makes it really, really strongly attractive to hydrogen ions. So hydrogen ion, a hydrogen ion, can attach itself to the water molecule, and when it does that, it will become H3O positive. Where'd the hydrogen come from? From the acid. The acid donated the hydrogen to the water, and the water became the hydronium ion. So anytime you put an acid in water, it's going to make a hydronium ion because the water is going to steal the hydrogen from the HCl. By the way, if you look at this, we still have acid-base chemistry and conjugate acid, conjugate base. Here's our acid. Water gained the hydrogen, so water's our base. This is the substance that gained the hydrogen, so now it's the conjugate acid. This is the substance that lost the hydrogen, so now this is our conjugate base. So water can act like a base when it's in the presence of an acid. The acid gives its hydrogen to the water molecule. Water cannot gain a fourth hydrogen ion. It can only gain one, become hydronium, and that's it. So for bases, we're going to talk about what bases actually do when you put bases into water. With acids, it's really clear. The acid gives away its hydrogen. With bases, there's a couple of different things. So with strong bases, if I put a strong base, let's say lithium hydroxide, and I place that in water, the lithium hydroxide is actually not going to react with the water. The water is simply going to dissociate the lithium and hydroxide ion. So I'm going to write water above the arrow here, just saying that it's not actually carrying out a reaction. It's just going to cause the lithium hydroxide ions to split apart. And so the lithium ions will break apart and the hydroxide ions will break apart. And this happens 100%. Every single lithium hydroxide ion is going to split apart when placed in water. That's what makes it a strong base. And any of these strong bases would do the exact same thing. The hydroxides would come off of their positive cations. So with bases, if it's a strong base, the ions just dissociate. But what about weak bases? Let's say NH3, which is one of the weak bases we've talked about. What is going to happen if I put NH3 into water? Well, it is going to react with the water because water can behave like an acid. So if water behaves like an acid, what does that mean water is going to do? That means water is going to give a hydrogen to our base. And so NH3 is going to gain a hydrogen from the water molecule, hydrogen ion, and now it's going to be NH4 positive because it gained that positive H. The water molecule then lost the positive hydrogen, and that leaves an OH minus because it just lost one hydrogen ion. And again, how does this happen? One of the hydrogens is capable of coming off, and this oxygen then can have that extra electron pair that hydrogen was sharing with the oxygen. So water is really unique in that it can go both ways when it comes to acids and bases. And that term we use for that is amphiprotic. Protic means proton, and amphi means both. So amphiprotic means it can give protons and it can accept protons. So our base here, our acid here, which is the opposite of what water was doing with the acid. This is our conjugate acid because it gained a hydrogen. This is our conjugate base because it lost a hydrogen. Now, if you'll notice, acids produce hydronium in water because acids always give a hydrogen to water molecules to make hydronium. And that's another definition of acids and bases that you are going to need to be familiar with. It's called the Arrhenius definition. And the Arrhenius definition says that acids produce hydronium in water. Bases, if you'll look at both of these examples here, bases produce hydroxide when they're placed in water. So both of these substances made OH, even though they made them in different ways, they both made OH when they were placed in water. And that's what Arrhenius said bases do. Bases produce hydroxide when they're placed in water. You're going to learn more about that later, but I did just want to point that out now. Acids produce hydronium in water, and bases produce hydroxide in water. So that is where I'm going to stop for now. That's a really brief introduction, but those are the highlights of acids and bases as an introduction. So good luck.